Okay, so today's topic is graphs, and I kind of have like an intro slide to kind of describe things here. One of the things we do in physics is try to figure out what has happened, and maybe more importantly, what will happen. Really good science should always make a prediction. For example, I did this one, done this one before. If I let go of my keys, make a prediction as to what will happen. No, they did not. Right? That's what good science should do, is should help you make a prediction. You say, well, they're going to fall, right? And one of the reasons why you know it's going to fall is based on experience, right? Experience would dictate that, well, every other time I let something go, it fell. In a way, you guys are on my 20-2 class for math, right? That's inductive logic, by the way. Or like, if it happened once and it happened again, and it happened a third time, and it happened a fourth time, eventually you start saying, well, it's probably going to happen the fifth, sixth, seventh, you know what I mean? Right? And if you can prove that deductively by actually coming up with the root causes for why something occurs, then that's really how like a law fits together. It's based first on observation, and then it's based on make a prediction, and then lastly you got to be able to explain, well, what the heck is happening, right? And when it comes to the keys falling, there's a theory that you probably heard about called gravity, right? And if we can explain how gravity works and make that logically fit with like the deductive reasoning, that's science, right? So the point I wanted to make here, though, is back to a graph. When you're looking at data, let's say that this is like a graph you've got going on here. Let's talk about the scenario and what's occurring here. This is a position time hand for a robotic arm during microsurgery. So you know how like a surgeon's cutting into a guy or something like that, right? Well, there are some things where they actually can use a robot to do surgery because the robot can make the just finest little incremental of movements that a person wouldn't be able to do, right? And like a person obviously still controls this from like a control room. So anyways, look at how this graph works. As it starts to move 0.2 millimeters, 0.4 millimeters, What's happening at the end here, though? Yeah, it's like it's not moving anymore, right? And so I have some words for that on the previous slide. Okay. One can interpolate is a word I'd like you to know. Interpolate basically means you use the graph and you read off of the graph currently being plotted. So if I were to ask you, where is the hand after 3 seconds? You look at the graph and you say, well, here's 3 seconds. You need to go after 3 seconds, it was right here. That's called interpolating, right? Where you use the data you currently have and you just kind of start with it. Does that make sense? But good science should allow you to go beyond that and start to extrapolate. Interpolate, extrapolate. Extrapolate is basically making a prediction about what's going to happen in the future. So does this graph go up to the 12-second mark? No, the graph stopped at 10 seconds. But I feel fairly comfortable in being able to say, I think I know what's going to happen at 12 seconds. Right, like if we put 12 seconds right here, based on the current pattern and rate of progression, it looks like it unless something changes, it's still flattened out and stopped. Does that make sense? So my goal today, basically, I actually have 2 goals. The first goal, though, with graphs is to help you guys be able to look at a graph and interpret what has happened and maybe even make a prediction about what will happen based on the current pattern. Now, there's one downside to this whole inductive logic thing, though. What happens if the guy who's controlling the arm all of a sudden slips and all of a sudden the thing just moves again, right? That could happen, right? But the idea behind this is to try to make a prediction based on at least the evidence we have. This is where things are going to go. You know what I'm So let's talk about some more graphs. So most of this is pictures here. There you go. Okay. So here's 2 typical graphs you guys are going to get on the test questions. Like I said, they're laid out for me. So all I really have to do is just show you how to answer them. So here's the 2 types. One's called a position versus time graph. One's a velocity versus time graph. And let's just try to figure out, based on what we know here, what we expect to have, what's happening. So what's happening right here at this point right there? Is the person moving yet? No, they haven't even moved yet, right? But then if it's position versus time, it looks like he walked a meter, and then the next second he walked a meter, and the next second he walked a meter. Right? This is a nice straight line. We have a word for it. When someone, is that one? Linear, that'll work, actually. From a math perspective, we call it linear, that's correct. From a physics perspective, we call it uniform motion. Do you remember that from our last notes? This would be considered uniform motion because he's always kind of walking the same speed, right? Like In 1 second, he walks 1 meter. In 2 seconds, he walks 2 meters. In 3 seconds, he walks 3 meters. So it's actually, you know how you call it linear? Linear things have a constant slope. If it has a constant slope, you are then going at constant speed. Therefore, you're going linear motion. So ideally, you'd be able to look at this graph here and tell me that, okay, this guy is walking at a steady pace. Now, that changes a little bit on a velocity time graph. Can you guys identify for me on the velocity time graph where he's undergoing uniform motion? Is it section 1, 2, or 3 where he's going at the same speed? On the second graph here, where is the van undergoing uniform motion? Girls. There's only 5 of you to teach it. Yeah, section 2 is where you're going to go uniform motion, right? Because what's happening here is he starts at 20 meters per second, and actually, what is he doing during section 1? Can you describe it? Yeah, the word for that is accelerating. He's accelerating during section 1. Then during section 2, he's now going the constant speed. And then what's happened during section 3? Deceleration. Until he gets to this point right here. What happens at this point right here? Good, he stopped. Yeah, exactly. Does that make sense? Like, you guys just need to be able to just look at a graph and interpret what's happening. So, the shape of the graph then kind of tells you stuff. If you were to have, say, a velocity time graph where the line was like right along the axis right here, in this example right here, he'd be literally not moving, right? Because there's no velocity whatsoever. You're just sitting in front of the firehouse, right? This graph right here, you're going at a constant speed because it's a velocity time graph, right? Because it's velocity and time, whatever that speed is, let's say this is 10 right here, he's always going 10. It's actually paddling in a kayak. Whereas here, this velocity time graph, here he's not moving at all, and he's getting faster and faster and faster and faster. So this last one would be accelerating. Next. Okay, so let's talk through this graph here then. What is happening during section A?
Deceleration.
Kind of. Why has the graph changed? Why is it not one of those L graphs? How did this all of a sudden become one of those T graphs? There you go, yeah. This is the guy backing out of the garage, maybe, right? Just looking at it there. Right? You got it right there, though, right? Here, he's going backwards. He's accelerating backwards. Then here, he's actually traveling backwards still, but he's not speeding up anymore. Then here, he speeds up even more going backwards. Right? Then here, he's still going backwards, but now he's going kind of at a constant speed. And then during this section right here, even though it's actually looks like it's one line, it's actually two sections here. You really got to consider this section right here. In this spot right here, he's still going backwards, but slowing down, yeah. At this moment right here, what happens? Yeah, he like, I don't know, pulls the handbrake, does a 180, turns around. Just for a brief moment in time, he's stopped. Does that make sense? And then now, he's accelerating forward. So, going backwards faster and faster, same speed going backwards. Speeding up in the backwards direction, same speed. Slowing down, but still going in reverse. Brief moment of stopping, pulls a brake, spins his car around Vin Diesel style in Fast and Furious. Right? Starts speeding up again, and then right here, then he's on cruise control. You guys feel like you could look at graphs like that and be able to interpret them?
Oh, yeah, sure.
Awesome. Okay, moving forward. Okay, this graph right here then is a little different. You guys remember how last year in math, we would have learned about quadratic graphs? This is kind of like half a quadratic graph, and how it has that like curvy sort of shape to it. Not all graphs have to be linear. Linear graphs usually mean that you're kind of doing something consistently, but this is a graph that's kind of a quadratic. What ends up happening on this graph here, see this is a position versus time graph again. So it's not velocity and time, it's position and time. Anyone want to hazard a guess as to what's happening in this scenario here? Okay, that's true. But is he going constant speed or not? No. Because if he was going at constant speed, it would be a nice straight line. So because it's kind of like curving like this, and he's getting faster and faster. Right? Like in 1 second, he went, say, 4 meters. And then in 2 seconds, he's now gone 10 meters. Well, he went from 1 and 4 to 2 and 10. That's a faster rate, right? And then in 3, he's now up to 20. That's even more, right? In 4, he's now up to, I don't know, 32, right? So the idea behind this one here, as you look at those points, is that you have a curved graph like this, it usually means that you're getting faster and faster. Okay, I know you're actually ahead of the curve in terms of what I was asking for here, but you hit on something that we need to know how to do. It's called slope, which we do slope in math, right? But the same sort of concept applies still when we're doing physics here. So one thing that you're going to be asked to do is calculate the slope of a graph. Before we kind of get to the rest of the notes, do you guys remember how to calculate the slope of a graph, what the formula is? Rise over run. Yeah, rise over run. It may even be in your formula book. Do you guys have that booklet? Yeah, don't break it. Do you guys still have that formula book that I gave you? I actually printed some color ones if you want to change it for a color. Sure. Yeah. Color ones. Everybody except for Buck. Okay, I'll use the old one here though. Oh yeah, there we go. It's on literally page 1. Can you guys see the turn to the inside cover here? Formulas and data. The very, very first thing it'll tell you is slope. Slope is rise over run. And it'll have like delta y over delta x, y2. You know what stuff like that? Yeah. So, let's just do a quick recap on this slide here about how to figure out a slope then. If you wanted to figure out the slope of, say, line A, you have to make yourself like a triangle out of it. Something like this. Like I would make a triangle like this and say that my rise looks like it's about 100. And then my run along the bottom looks like it's about 20. And then I divide those two numbers and find that the slope is 5. That makes sense? Okay. If I were to do the other graph, the blue one, blue's a little bit trickier because I have to start here. So on the blue graph, it looks like my rise is about 110 maybe. Along the bottom of my run is from 5 to 20. Does that make sense? Not from 0 to 20 because it doesn't start at 0. So 15. Right, and then whatever that is, that's your slope. Straight enough? Fair enough? So, anyways, the thing I need you guys to know then is when you calculate the slope means something. So if you want to highlight a couple of things here, if it's a position time graph, your slope is velocity. If it's position time graph, slope is velocity. And then I have this one down below here. But on the other type of graph that we're going to do in this section so far, if it's a velocity time graph, the slope is acceleration. So if you have position and time and you calculate the slope, it's how fast you're going. But if you have a velocity and time graph and you calculate your slope, it's actually how much speeding up you're doing. So, by the way, guys, if you want to write stuff in these books here, feel free to. So if you want to like write that in the margin somewhere for tests and stuff, I'm okay with that. Read the book. There's like so much stuff in there. Okay, one more thing you need to know how to do. It's called area under a curve. And while I'm highlighting stuff here, I might as well do a little more color here. We've never done this before in math, but I promise you, you guys will be able to figure out how this works. Do you want a second to write that? You guys will already. I'll pause. Okay, so here's the third one. This one's not about slope, it's about area under a curve is what we call it. A curve is just a fancy word for a line. Not all lines are necessarily straight lines, if that makes sense. So we just use the general term curve. So the idea though is that if you have a velocity time curve and you find its area, It's the displacement. So I'm going to show you how to do that in this example here. Let's say I asked you, according to this graph, how far you traveled in 8 seconds. Okay, I'm just going to make up a question. How far did you go in 8 seconds? It's a very typical question. You finished?
Yeah.
You guys gonna stick around the building or sorry, what was that?
No.
Alright, just make sure you sign the board then. Thanks guys.
Bill, George.
Okay. So for this question right here, what you have to do is you have to make like a geometric shape out of this. So see how 8 seconds is right here? I'm just gonna draw a line straight up at the 8-second mark right here. And what it's gonna do is it's gonna create a box. You can see how there's kind of like a box that I'm kind of coloring in here. Okay. What's the area of a box? What's the formula for that? Yeah. So if the area of a box is length times width, we just need to know what those numbers are. So what is the length of this box? Or, I mean, just one or the other. I guess in terms of this side right here, it's 2.2. Does that make sense? I'm going to throw on a unit though. This side right here is 2.2 meters per second. How wide was our box across the bottom? Yeah, and by the way, the 8 seconds, I will have to tell you where you're stopping because I could have stopped here at 4 seconds. I could have stopped here at 10 seconds. So you do need to be told where to stop. But hopefully you agree that it was 8 seconds. Now watch this, look at the units here. If you have 2.2 meters per second, if I write it a little bit differently, and write it in like this kind of format here where I go meters over top of a second, if I write it like that, can you guys visualize how that seconds and that seconds will cancel? And I'll be left with, I think it's going to be 17.6 meters. Just grab a calculator and confirm that's what 2.2 by 8 is. 17.6. The key here, do you guys see how the units kind of cancel? Yeah. Right? And what we're left with is meters. So in 8 seconds, you traveled 17.6 meters. Right? So then if I were to ask you, well, how far you traveled in 10 seconds, well, then you'd change the size of your box. Okay. Now, boxes work really well if you have a really very flat line across. But I can't guarantee that every graph is going to be a flat line. So I might give you a question like this one here, where it's got some sloped lines as well. So let's try these 2 questions now. This is a very typical kind of 2-parter question. I give you a graph, and we've already looked at this graph before. Like this isn't a new one. This is one we already used. Right here, speeding up. Right here, constant speed. Right here, slowing down to a stop. So my 2-parter question. First, let's find the deceleration of the band. Where is the deceleration of the band section? 1, 2, 3. Okay. How would you calculate an acceleration or a deceleration on a velocity time graph? Nope, not that. Look back at the notes you guys just wrote there, like because you wrote it in your books there. If you want to calculate an acceleration, what are we looking for? The slope of a velocity time graph. Because you guys probably wrote something like that down just a second ago in your books, right? Or what did you write? Velocity time graph slope is acceleration. Did you write something like that? Right. So we have a velocity time graph, right? If we want the acceleration, we need the slope right here. Okay. So let's make a triangle out of it. Here is a triangle out of it, but we're not doing, like you suggested, 1/2 base height. That's not what we're looking for though. That will find us something else. If we want the acceleration, we have to do our rise over run bit. So our rise goes from 30 down to nothing. Technically, we should make that -30 though, because you know how it's going like downhill slope. So the rise is -30, and then your run from 30 over to 45 would be 50. Watch the units here. The rise is in meters per second because that's the units of the up and down. So that's in meters per second. Your run is in seconds. So when you divide 30 by 15, you're going to get -2 because 30 over 15 is 2. And then the unit now is going to be meters per second squared. That's an acceleration value. So you're slowing down the 2 meters per second squared. That's how you calculate it. A lot of my kids, when I teach them this in their physics 20 class, they actually find this very frustrating because there's like no work to it, right? Like it's all just, do you understand how graphs work, right? Like the only thing you have to do is just divide two numbers. Does that make sense?
Yeah. Why is it?
Say that again? Because it's going like from start to finish, like it's going from 30 down to nothing. How do you get from 30 down to nothing? Well, you have to subtract 30 to get from 30 down to nothing. Does that make sense? So, lines that go like this have a negative slope. Lines that go like this have a positive slope. Alright, so there's the first one. So then for the second one, we want to find the distance traveled. If you want to find the distance traveled, the way you do that is you find the area under a velocity time graph. Okay, so the three things. If you want to find acceleration, it's the slope of velocity time. If you want to find velocity, it's the slope of position time. And if you want to find distance, it's the area under velocity time. So we got to find the area here. However, this one's a little more challenging. There's not actually necessarily just one shape. I would argue that we've got 4 shapes. See how I've kind of made 4 different shapes out of it? I've got a little triangle right here. I've got a rectangle here. I've got a square-ish looking thing here. And I've got another triangle there. So I need to find the area of all of those shapes. If I put all that area together, that'll tell me how far I've traveled. Does that make sense? So let's try it one more time. Triangle 1. The formula for a triangle is 1/2 base times height. Let's see, the base of this little bitty triangle looks like it's 5. And the height is 10. Makes sense? 5 by 10 is 50. Half of that should give you 25. And the unit, by the way, then would be meters. And the reason why is that this guy is in meters per second. And you're timesing by seconds. I already kind of showed you this. The seconds will cancel and be left with meters. So I don't need you to show me that. I just know that that's what it's going to do. So there's our first section. In this little bit right here, he's traveled 25 meters. But I have to account for the fact that there's also this box underneath it as well. So in box number 2, we just need like length times width, I guess. The length of the box, I don't care which one goes where, right? One was 5, the other one looks like it's 20. So 5 by 20 leaves you with 100.
Doing physics first.
With these guys, yeah. You guys okay with that so far? Okay, third one is also a length by width box. It looks like it's got a height of 30, right? So 30 is one of them. I know it ends up at 30 right here, but it's not 30. 25, you catch that. I don't know off the top of my head. 600 maybe? 750. Not even close. Oh, yeah, 30 by 20 would be 600. You guys still good with me? And then for the last one, 1/2 of base height is number 4. 1/2 of base height, so it's 1/2 of, what's that height again? Still 30? And the base is 15. I got 225. Any thoughts about what I should do with these four numbers I've calculated? That's it, yeah. Add them all up, yeah. Because that's how you find the area under a curve. So let's add them all up. 25 plus 100 plus 750 plus 205. I got 1100. Is that much?
Yeah.
Thank you, guys. Oh, name. Oh, that's wrong. Okay. So, quick summary of what we've done so far then. I need you to know how to do three things using a graph. Okay. First one, if you want to find an acceleration, you need the slope of a velocity time graph. If you want to find velocity, you need the slope of a position time graph, or like distance time graph. And then finally, if you want to know how far you traveled, your distance, you need the shape area underneath a velocity time graph. So if you guys did, I mean, yes, you guys already wrote two of those down in your data book, right? So if you want to write the third one down, if you haven't, have you done that already? So the third one, you know how you already wrote down two of them from my previous slide? The third one then would be, if you want to calculate a distance, you need the area under a velocity time graph. That makes sense. So velocity time graphs are good for two things. They can get you the acceleration by the slope, or the distance traveled by the area. Whereas if you have the position time graph, the only thing it's good for is velocity. If you find the area under its graph, it doesn't mean anything. Sound good? Okay, so that's kind of the first part of the lesson, is trying to work with graphs. Okay. The second half of the graph, second half of the lesson kind of builds on it a little bit here. I just kind of have a new cover slide here. You know how we just finished calculating how far distance-wise you traveled? The one thing your textbook does a lot of is they want to relate this unit to the transportation industry. You can kind of see this even with the project that I'm giving you guys. The idea of collisions and vehicles and speeds and car crashes and stuff like that, right? So I found this picture right here. Here's a vehicle that, based on the skid marks it just provided there, looks like it had to stop on a dime, right? Like it's trying to come to a stop really quickly. And so if you want to figure out how far something has traveled, that's quite an important thing to do, right? One way you can do that then is using a graph. I'm going to show you a second way, which involves using some formulas. Okay, so I got some formulas on the next couple slides here. Before I get to that, there's basically four main variables we can work with. We can talk about distance or displacement, speed or velocity, acceleration and time. Those are kind of the main things we talk about. Guys, what's the difference between distance and displacement?
Displacement has it.
Yeah, like this one right here is a vector. Same thing with velocity, it has a direction, it's a vector. Does that make sense? So, the last thing I need to show you then is all the formulas we have. You guys have those booklets I just gave you. Can you flip to like the second maybe page inside there? It lists a whole bunch of them. We're going to be learning them, I guess, slowly over time here. So like the very first two we've already talked about. V equals D over T, V equals D over T, and then like A equals V over T. Skip down a couple. I don't know why they put them in this weird order, but for whatever reason they did. So skip over the F net one, over the F net one, over the W one, over the P one, and look at the two after that. You guys see there's a delta D equals VI delta T plus 1/2 8 of T squared. And the one below that is VI plus VF over 2. Those are the next two formulas I need to show you, where they don't involve new letters, right? Like they still involve the same combinations of distances, velocities, accelerations, times, right? It's just they're rearranged differently. Have we talked about the I and the F and what that means? Fantastic, good, okay. So my last little bit here is just to give you guys some practice, and this will probably be your least favorite part of this, but the good news is this is about as hard as it gets. We need to have good algebra skills to be able to use these formulas and rearrange for whatever we need to solve for. But I'm pretty confident you guys will be able to do this because it's a way lower level than what we even had to do in our like -2 class. So let's try some examples. Let's say that you've got a car traveling behind a slow vehicle, right? You've probably been here before. The guy in front of you is going 90. You're like, speed up. I mean, unless it's winter, and then maybe that's okay, right? So What do you do? Well, you pull over and you want to pass them. Right? That's logical. And I don't know, somehow your car measures that you're accelerating at this speed, right? Because you have to speed up to pass them, right? You can't just keep going 90 and expect to pass the guy. You're going to have to speed up, right? So you accelerate at this rate, and it takes you 5 seconds. My question here is, how far has the vehicle traveled, right? And you can maybe imagine where this would be an important scenario. It's maybe not such a big deal in Southern Alberta where we have these double-lane highways, but I grew up in BC where we don't have any double-lane highways. And when you want to try to pass somebody, you have to pull into oncoming traffic sort of scenario, right? If there's a car coming towards you, you have to have good judgment skills to figure out, can I get around this guy before that head-on car crashes into me? You know what I'm saying there? Right? And so knowing how much distance you have, you might know, like, I've got to get around this guy by this point here, because if I don't get around this guy by that point, the car is going to cause a problem. You know what I'm saying? So, it's actually fairly easy, minus just the, you got to be good at algebra part. So, here's how I like to show my my physics 20 kids. So I'll do the same thing with you guys. I like to write out, right off the bat, the information I have. So let's start with the first one, that 90 kilometers an hour. What kind of variable is that? Like what letter would that represent? A, D, F, A, D, E, T. Is that a speed?
Yeah.
Okay. Is it an initial velocity or a final velocity? Is 90 kilometers going to be his initial and his final speed? Because he has to go faster than that, right? So he's starting at 90. That makes sense? That's his start speed. All right, then the next number we're given is this 0.50 meters per second squared number. Sorry, that wasn't overly nice one. What does that represent? Distance, time, velocity, acceleration? Good, yeah. Then it gives us a 5.0 seconds number. What does that represent? Time, yeah. And then for the last thing, usually you're given like a couple of different values here. There's always one thing that you're looking for. So I always just put I just put a question mark or a couple of them next to the last one. And the first thing we're going to look for is how far the vehicle has traveled. We'll make that one first. So if we're asking how far it's traveled, we're asking for, well, what is the distance? Okay? So I like to start here, just write out what sort of information we have that we're working with. The next thing you got to do then is go to your formula section and figure out which of these formulas here involves the variables you have. Okay. Like for example, I'm going to show you which one not to use. Don't use this one. And the reason why that one's no good to you is that you do know time. Time was a number we knew. And you do know velocity initial. But you don't know velocity final, and you don't know distance. You know what I'm saying here? And you can't have two things you don't know. So you have to pick a formula where you know everything except for one of them. And so hopefully you're kind of figuring this out here. The formula above it's really good for us to use because we do know the velocity initial, because that was 90. We do know time. We do know the acceleration. And this will just use this time a second time. Does that make sense? So let's write out that formula there. D equals VIT plus 1/2 AT squared. Do you guys ever do this in Science 10 actually? This is a formula that I gave you in Science 10 actually. You weren't in my Science 10 class, so. There's one issue though. And this is actually why there was a question on your assignment about this. We have to make a conversion. Your units have to be compatible. See how these right here are in meters per seconds, and this is in seconds, but this top one's in kilometers an hour? We can't have one be in meters per seconds and one's in kilometers an hour, because then the units won't cancel properly. So we have to make a good conversion, which is why that was a question on your assignment already. But you guys did this, right? 90 kilometers an hour. What should I do to get rid of, let's say, the kilometers? Where should the kilometers go, top or bottom? Okay, what should you put above? Meters. Because we want to get rid of kilometers. Oh, sorry. And then what's the ratio? Where does the 1,000 go? On the top or the bottom? Good, okay. Does that make sense to you guys? So now we have meters per hour. Then we want to get rid of hours. So put hours on top. You can go to seconds directly if you want. Do you guys know how many seconds are in an hour?
36.
That'll work, yeah. Or you can just do 2 sets of 60. I think I did this with a couple of you guys. We just did 62 different times. But if you want to, you can just say in 1 hour, there's 3,600 seconds. That works too. There's actually, I was looking through this book here. There's actually a sheet out there that tells you that sort of stuff. Just in case you don't know. Where was it? Second page?
Or the first page.
Yeah, there it is. Can you guys see like at the bottom there? It says some non-SI units used with SI. It's got like time there. So if you ever need to know those like equivalencies, there's some there. It's got minute to seconds, in case you don't know, right? Hours to seconds, days to seconds. Years, they use A for years. You ever heard that before? 3 years. So anyways, if you ever need to find that, you can just go right to that one. Anyways, I need you guys to help them. Can someone take 90 times by 1,000 divided by 3,600 for me? I'm fairly certain it's 25. Just because I have that one memorized. Just double check in case I screwed up. Yeah, that's 25. The reason I have it memorized is because when you do the conversion between meters per second and kilometers an hour, there's like one number that like, it's like even numbers on both sides. Like if you do 60, it gives you like 19.2 repeating or something like that. But like the one that has whole numbers, I just memorized it. 25 to 90. Anyways, we have what we need now to get started. So let's plug this in here. Your velocity initial is 25 meters per second. Your time is 5 seconds. Your acceleration was 0.50 meters per second squared. And then your time was 5, then you have to square that. Does that make sense? I'm just kind of plugging everything into the formula there. And all you just need to do is know how to put it in your calculator. So it'll look something like this. This one's quite nice because you don't have to do any algebra to kind of work backwards for anything. Like it literally is ready to go as is. So you just got to do 25 times 5 plus 1/2 times 0.50 times 5 squared. Good. Now you know how much distance you need. You need 131.25 meters. That makes sense? Okay, there was a second part of the question here too. Sorry guys. The second part of the question here is how fast will you be traveling when you're done? So if it's okay, I'm just going to erase, so I have room here, but don't you erase stuff, I'm just going to erase it down below here. Okay. Now what I did is I took off the D, because D is what we were looking for last time, but rather than looking for D, now let's look for velocity final. You know what I'm saying? Right, because nothing's changed. You still started at 90 clicks an hour. You still accelerated at 0.5 meter per second squared. That got erased. Still takes you 5 seconds, but now you're looking for another variable. So what we need to do now is just figure out, well, which of those formulas is the one that's useful to us in this scenario. Does that make sense? So I'm going to go back then to the slide right here, and I need to find a formula then that has velocity final in it, but also has that other information. Which one might be useful? There's actually 2 choices. Actually, 2 different ways you can do this. This one down here in the bottom corner. Because we know time, right? 5 seconds. We know velocity initial. And didn't we just find distance just a second ago? So even though I don't have it written down on my list right here, I kind of could write it in there because the distance was 131.25. Is that what it is? So the challenge though is, do you see how this VF sitting right here is not by itself? That's where your algebra skills come in. Okay. I'm not talking crazy like it was in Math 20 where you have to like do common denominators and factor and stuff like that. But you do need to know the right steps to solve. So let me write it up then. So the formula that we're picking was D equals, oh goodness, big bracket VF plus VI all over 2 times time. That's the formula. Okay. Most kids, when they do this, they prefer, but there's 2 ways. You could do all the rearranging now, or you can plug in your numbers that you have and then do rearranging. I prefer that myself. So I'm going to start plugging in some numbers, because I know some of them. Like, this D is 131.25. The velocity final is the thing that I don't know. Velocity initial was 25. And the time was 5. So all we have to do now is do our algebra to isolate for what VF is. So give me some thoughts. What's the first thing I should do? Actually, no, take it from this here. I have 3 numbers I have to remove to get VF by itself, correct? I have to get rid of the 2 off the bottom. I have to get rid of the plus 25, and I have to get rid of the 5. One of them has to be last. Which one has to be last? Not the 5. It's the plus 25. It's a binomial. Essentially, this VF plus 25 is a binomial. That kind of takes precedence. So I have to get rid of this 5 and that 2 kind of first. I would get rid of the 5 first myself. Like, I would divide both sides by 5. Like that. Now, I'm not actually going to type it in my calculator until I'm done, so that's just wasting time. Right, now see how there's like the 2 on the bottom here? To get rid of the 2, then I'll times both sides by 2. I'll get rid of that one. And then you see how now we've isolated the binomial by itself now? How do you get rid of the plus 25? Say that one? Yeah, subtract 25, yeah. So, I mean, my work is not exactly the prettiest right here, but can you guys follow how we're pulling this off? So, go to your calculator. In order to undo this, you have to take your 131.25. You have to times by 2. You have to divide by 5. And then when you're done, we need to subtract 25. All of that is equal to 27.5. That's meters per second, though, by the way. Which means that you were going 25 meters per second, and now by the time you're done, you're going 27.5 meters per second. So you're going faster, which you should be, right? Because you're passing the gap. That makes sense. That'll probably be one of the hardest things we do. If you can handle that, you're golden. It is something that we're definitely doing. I mean, not all these formulas that are in this data booklet are in the 20 course. So if you guys do end up taking Science 30, you know, like all these formulas in here, you will have to use them all at some point. But those are probably some of the hardest ones that are in there. Right? As long as you can handle that, you're pretty good. These are loud. All right, let's try another example. Diver steps off the edge of a platform, falls into the water 3 meters below. If the initial velocity of the diver was 0, how long does it take him to hit the water? Essentially, the idea is just like me dropping my keys. I'm going to drop my keys, and they're eventually going to hit the floor below. The question is, well, make a prediction. Remember that idea of where I started class, the idea of interpolate and extrapolate? Extrapolate should be able to mean, well, tell me what's going to happen in the future. My question for you is, when will it hit the ground? Make that prediction in the future. So let me do the same task I started with. I'm going to start writing out what I know. This 3 meters below, what is that a measure of? Is that like an A, a D, a V, or a T? 3 meters. Acceleration, velocity, distance, or time? Distance. Yeah, it's a distance. So the distance you're going to travel is 3 meters. It actually, that's the only number there. There's actually two that are hidden. One of them is right here. The initial velocity of the diver was 0. It's really sneaky, but there is a velocity initial of 0 meters per second. Because he's literally just stepping off the diving board. There's actually one more number that's implied. They kind of expect that you guys remember from grade 10. It's the acceleration. Do you guys remember what a gravity acceleration number is? 9.1. Yeah. Let's look for that in your data booklets, and if it's not in there, we need to write it in there. But I'm sure it's in there somewhere. It's got to be. Oh, there it is. It's in page 2 at the bottom. It's the under the astronomy data. It's the average acceleration due to gravity on the surface of the Earth equals 9.81 meters per second squared. You guys found that one there? So you'll be expected to just know that that's acceleration if things are falling. So the last thing we're looking for then is time. We need to calculate time. So we need to pick a formula that has all of these variables in it. I mean, obviously I'm picking the new formulas because those are the new ones for you. So this is the one you need. D equals VIT plus 1/2 AT squared. That's the new formula because it has all those, right? It has a distance, which we know is 3. It has a velocity initial, which we know is 0. We don't know time. That's okay. Well, there's one thing that we're allowed to have be the one we don't know yet. We know the acceleration, 9.81. And time, we still don't know it, but at least there's only one variable left. So I'll start throwing some numbers in them. This is going to be 3. This one's going to be 0 times t. And then this one is going to be 9.81, and that's going to be t squared. So far, so good? So we need to have our algebra skills. We need to get t by itself. In 20-2, you guys would have learned the quadratic formula. Now, we actually don't have to use the quadratic formula here, because I'm going to show you a nifty little trick as to why it won't be necessary. But you can see how it's kind of quadratic in a way, because you have x and x squared, only we have t and t squared. So the quadratic formula could be the way that you solve this. You just have to rearrange it, but this is really clever actually. See how there's a 0 times by t? Isn't 0 times by t just going to like make that nothing? Well, now I don't have multiple t's left over, I just have this guy right here. So to get rid of all the numbers surrounding it, I have to get rid of the 1/2. To get rid of the 1/2 times both sides by 2, I'll get rid of the 1/2. To get rid of the 9.81, divide both sides by 9.81. How do you make it so that it's no longer t squared? Square root, there you go. It's actually kind of good that we did math before science, just because you kind of use the skills from math in the science course, but like probably not to the same degree of difficulty. So we take 2, we times by 3, we divide by 9.81. And then if we square root the answer, there. Time is, let's call it 0.782 seconds. Is it go follow it? Okay, I think this is my last set. No, I got 2 more left. Okay. Sorry, this is kind of, these are going to be days where we're probably talking the most class. I'm sorry in advance. Back to like driving, because that's kind of where the textbook, like when you guys read through the textbook, that's what they seem to focus on all the time, is just cars that crash and stopping time. But a very thing that you might have to find is what's called a stopping distance, where as you approach the intersection right here, let's say that the lights turn in a different color, right? You got to figure out where is your point of no return. You guys have all been through driver something training, right, before. Like when you're about to go through an intersection, you've been taught. You know who taught this? That like you have to make a determination as to like where your cutoff point is, where it's like either you got to gun it at that point, or you got to start hitting the brakes. You got to make a choice, right? You can't just be in no man's land.
I just stop and
Just
I
stop in
get
the middle.
too scared. I just
Fucking stop. Right. So the idea is basically what is your stopping distance? Like if you saw the yellow light when you were right here, could you still stop in time? If you could, you're supposed to start stopping, right? Whereas if you saw the yellow light right here, there is no way for you to stop in that short period of time. You may as well run the yellow, right? So I got two last examples here. First one here, it says that the reaction time for most drivers. The reaction time for most drivers is it's supposed to be about 1.5 seconds. So what that means is it takes you about 1.5 seconds to first have your brain process that there's actually something wrong, where you go, there's a car accident ahead, right? But then the other part of it is not only for your brain to process it, but for you to get your foot to the brake. Most people, it takes them about 1.5 seconds to get that far. Okay. So let's say the car is able to decelerate at this rate here. We want to figure out the stopping distance for a car traveling 125. So this is actually a two-part question. In part one, we need to figure out how far you go before you even hit the brakes. Does that make sense? Because you're going to be coasting along at $1.25 for a little while before you even get your foot to the brake. It takes you a while just to get to there. Does that make sense? That's part one. And then in part two, then you got to figure out how far you go while you slow down. Because you don't just instantly stop when you put your foot on the brake, right? It takes you a little while. So there's actually two different parts to this. How far you go before you even hit the brakes, and then how far you go while you're slowing down. We got to combine those two things together. Sound good? Okay, so let's list out what we know in the first section here. Before you even hit the brakes, there really is no, well, there's a time, right? The time that it's going to take you to hit the brakes is $1.50 seconds, right? We know that much. We also know your velocity, but this is a little bit different here. It's not a velocity final or a velocity initial, because it's just a straight up, you're going the same speed the whole time. So I'm not going to put a VF or a VI next to it. I'm just going to say that you're going 125 kilometers an hour as your velocity there. Right? I don't need to put an F or an I because you're going the same speed the whole time still. And then the last thing is we're going to find the distance that you traveled during that. Is there a formula that just involves D? Yeah, it's the V equals change in D over change in T formula. Okay, I got one problem though. $1.50 and 125 have incompatible units though, so we can't use two different unit types. Does that make sense? So we have to convert the 125 kilometers an hour. So, I mean, we did this a little while ago, right? 125 kilometers per hour multiplied by 1,000 meters in a kilometer multiplied by, in 1 hour, there are 3,600 seconds. That's what I got, 34.72. Okay. When you guys are doing your calculations, you should always use like the whole number if you can. So don't just round to 35 or 34. Like try to use the 34.72 number when we use that. Rounding leads to errors. Okay, so we actually have all we need to use that formula. We know the velocity is 34.72 repeating. We want to find the distance. We know the time is $1.50. I'll take off a second. Oh, maybe the units there. So algebra, how do you get distance by itself? Just times it up, yeah. So take that number times by 150. I got this, a distance of 5208 point. Oh, hang on, that's all right. I missed the 1.50. 1.50. 52.08. 3 repeating. There's a decimal sitting there. Does it follow that so far?
Is that 53 repeating?
Yeah, I like it's repeating. I just didn't write the bar. So based on what we have so far there, this is before you even get your foot to the brake, right? Like this is you driving along, la 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 la, cell phone out, hopefully not, right? And it takes you 1.5 seconds just to get your foot down. 50 meters has gone by, right? I mean, I don't know if you guys run track or stuff like that, right? But like that's half of a 100-meter dash. That's how far you're going to go before you even can start braking, right? This is one of the reasons why there's such big pushes to get kids to not be on their cell phones, right? Because 150 seconds is bad, but like let's say you're down like this, and 1 Mississippi, 2 Mississippi, oh crap, right? Like it's even worse if you're even slower than that because you're on your cell phone. So because now we have to get to the second part of it. Now you're actually going to start braking. How long will it take for you to start braking as well? So that was part 1. Now we need part 2. Okay, so let's talk in part 2. In part 2, we know your velocity initial because you know how fast you were originally traveling. You were traveling that 34.72 meters per second. We know that much, right? We also know the velocity final. It doesn't say so, but if you're going to eventually come to a stop, what's your eventual final velocity would be? 0, yeah. We need to know at least something else to make this work, because we want to know distance. But as I look at this right here, the other number we have here is the deceleration of 5.25. So I do have that deceleration number right there. Except I shouldn't use 5.25. I didn't make a negative. Why? Yeah, you slow it down, right? If you use positive 5.25, this would be you coming across an accident. You're like, oh no, there's an accident here. And you accidentally hit the gas. That's going to cause bigger problems, right? So we do need to be negative. Okay. Okay, I'm probably only out of time to finish this example. We'll have to leave the last one until another day. Sorry. Do we have a formula that uses these 4 things here? VI, VF, A, and D. Look back on those 4 formulas. There actually isn't one that involves them all. So what we're going to have to do instead is first we're going to have to solve for time. And we're going to have to figure out how long it will take for us to brake. So we should be able to find a formula that uses VI, VF, A, and T, because that formula is this. Acceleration is equal to your change in velocity over your change in time. So my acceleration is negative 5.25 meters per second. Well, let's get rid of the units. I'll just use the numbers. On your formula sheet, that one with acceleration, does it do like VF minus VI? It does too. You see on the formula sheet it's VF minus VI?
Yeah, where is it?
Second page on your formula sheet. Third formula down? Fourth formula down?
Yeah.
Third one down. See how it goes VF minus VI? Yeah. Okay. So your velocity final is going to be 0. Your velocity initial is going to be 34.722 repeating. And we're looking for delta T. How do we get delta T by itself using our algebra skills here? You swing the delta T up to the other side, like you times this one up here, but then you take the minus 525 number and you bring it back down and it's close. So delta T is going to be, okay, 0 minus 34.72. Isn't that just going to be minus 34.72 repeating? Divided by minus 5.25. Here's why that minus is so important. two minuses divided by each other makes a, which is good because time should be positive.
When the 5.25 become a
You're dividing it though, not adding. You're dividing. So make minus 34.72222 repeating divided by minus 5.25, and I've got a time value of 6.6137 or so seconds. Yeah. So based on the conditions that we were at least given here, not only is it going to take you a second and a half to just start seeing the accident, but if your car can actually decelerate at this rate, it's still going to take you 6 seconds to stop the car. The question is, how far are we going to travel during that time? So here's our last step. There's a lot to do. Now let's use the formula D equals VIT plus 1/2 AT squared. We use that formula. Because I want to know the distance, right? But I know my initial velocity. I was originally traveling 34.72 repeating. I know how long it's going to take me because time I just found a second ago was 6.6137, something like that. Here's the really important one. You know when you use this acceleration right here though? Use the negative number. So I'm going to make that minus 5.25. And then I have to do time another time, so 6.6137 squared.
Whoa.
Yeah. This is probably the hardest of what we end up doing. It's where you're using like multiple ones of these formulas. So let's try this. 34.72 repeating times by 6.6137 plus 1/2 negative 5.25 6.6137 squared. It's going to take you another 115 meters to slow down.
You're not going to try this.
Well, this is why people usually end up rear-ending other vehicles, right? Now, I'm not saying, like, let's say that you, like, when you add these together, right, you've got, this is 114.8. The other number was 52, let's call it. Right, so when we add those two numbers together, you end up needing about 167 meters. Okay. Now, this is why a lot of cars will get into at least some sort of accident, a fender bender. Because let's say that you don't have 167 meters to stop, you only have 150 meters to stop. Yeah, you're going to hit the guy in front of you, but you're not necessarily going to smoke into him. It just means you're going to hit him with like 5 to 10 kilometers an hour. You know what I'm saying there? As you're slowing down. So, which still causes whiplash, right? The guy who gets hit in front of you still causes a problem, right? So this would be the safe distance you'd require to have no accident whatsoever.
Wow.
Okay, I'll leave the last question for now because it's going to be a lot anyways. Quick summary of our data. There's really two parts to it. Part A, can you look at a graph? Can you figure out the three things off of a graph? Can you find the slope for either acceleration and velocity or the area for distance? That's the first one. The second one's probably the harder one. Can you use the 4 formulas on your formula sheet to solve a question? And sometimes you have to use multiple formulas to solve questions. Like sometimes it'll just be one step and it'll be easy, but you need to know how to use all 4 of them.
That sounds hard. It's easy to do, honestly. I'll get
Okay,
it.
last thought here, and then you guys can probably take off. Let me just look back at the assignment again now and talk about what you can solve. Okay, so here's the assignment now. Hold off on this one here involving force. You can come in, we're not quite done yet. Hold off on 9 and 10 involving forces, but you guys should now be able to do like this number 11 one involving graphs and looking at them. And all of the ones on the back page are pretty much what we just talked about, where there's a car driving and then it needs to react and then it needs to eventually brake. And so you can do some of these questions here. You might even be able to do all of them except for this one involving Newton's laws, which we're getting to next week. Okay. Final thought. This may not be enough practice on its own. You guys should really try a couple of the questions in like the textbook. If you want, I'll find you some. But you probably can't do well at this just walk into it cold. So if you want more practice than this, let me know. I'll find you some in that textbook.
Okay. Sounds good.
Okay, we're done.